very much for joining us today for the public lecture by Dr. Neta Bahcall. So Dr. Bahcall is visiting UT Austin this week as the distinguished recipient of the Antoinette de Vaucouleurs Memorial Lectureship and Medal. And I want to say a few words about Antoinette. So this award honors Antoinette de Vaucouleurs, and she was a UT astronomer who achieved international recognition for her work as a professional astronomer already in the early 1950s, when there were very few women actually working in the field of astronomy. And she's contributed to a lot of foundational work, pioneering work in galaxy evolution. And this lectureship and medal was established by the UT Board of Regents, also friends of the astronomy department and members of our wonderful Department of Astronomy and Bahcall Observatory Board of Visitors. And I know many of you are in attendance today, so thank you for joining us for this award and this public lecture. And each year we give this award, we give this lectureship and this medal to an astronomer for outstanding contribution to astronomy. And yesterday we had the honor and the privilege to award this to Dr. Bahcall in the department, and she gave a wonderful colloquium. And she has been very graceful and agreed also to give a public lecture today. So I want to say a few words about Dr. Bahcall. So she received a PhD in 1970 from Tel Aviv, and she worked on nuclear astrophysics under the supervision of Dr. Fowler, Professor Fowler at Caltech. Once she finished her PhD, she continued her career. She moved to Princeton first. Then she moved to NASA Space Telescope Science Institute, and then she returned back to Princeton on the faculty. And she's now the Eugene Higgins Professor of Astrophysics at Princeton. And those of you who know Neta, throughout her career, she has been really a trailblazer and a pioneer. And I will just cite a few examples. It will take the rest of the lecture if I were to give you all her accomplishment, but there are certain few things I would like to highlight. So today we have NASA Space Telescope Science Institute, and it's a major scientific powerhouse for astronomy. It runs the Hubble. It's going to run the next generation James Webb Space Telescope. And Dr. Bahcall played a major role in the early success of the institute. So she joined the institute when it was just starting. It had about 15 people. I worked at the institute about 10 years ago. It had more than 200 people. So when Dr. Bahcall was there, it was really starting, and she was the first head of the Science Program Selection Office and the chief of the General Observer Branch at the Institute. So these programs and many others that she shaped have become what I would call the gold standard in astronomy. They have shaped many programs that NASA and the National Science Foundation run today, the large science survey, and they are really shaped after Neta's early models of how they should be run. Her research program has also been absolutely foundational, and it addresses a number of questions that you will hear about in the lecture today. What is the large-scale structure of the universe? What is the dark matter content of the universe? Where is that dark matter located? What is the nature of dark energy, this mysterious force that is causing the universe to accelerate? And what is the fate of our universe? This is eventually what we would all like to know. And she works very closely with a graduate student. I see many students in the room today. So Dr. Bahcall works very closely with a graduate student and postdoc. And this collaboration with her students and her junior members in her team has led to publication of over 300 papers on these subjects. And to me and to many astronomers, what is really remarkable is that Dr. Bahcall was really one of the early and strongest proponents of a universe that has the following features. It only has a moderate amount of matter, what astronomers call omega matter 0.26. It is accelerating, as we know from the Nobel Prize in 2011, and it is dominated by dark energy. Now, this model is accepted today, right? It's the standard paradigm. It's what we all know, what we accept, and it's been confirmed by many observations. But when Dr. Bahcall presented these models, it was very controversial. And so she stood her ground and she defended this model, conference after conference. I was a graduate student in the 90s, and I went to a conference and saw the heated debate. So when I met Dr. Bahcall on Monday, I asked her what is it that drove a sense of conviction at the time that she was right. And she gave me a wonderful answer, and I was so enamored by this answer, I'm going to say it again. So science is a wonderful process that constantly evaluates again and again what we think we know. And if one looks at the data, the truth always comes out. And that's what she did, as you will see in her lecture. She really looked very carefully, very precisely at the data. And her 1999 article in the Science magazine has been cited over 900 times on this topic. So she has received a very long list of awards, and I will just touch on a few of them. UT Astronomy, we have a Texas-sized flair for talent. So we already recognized Dr. Bahcall at a very early stage of her career. In 1988 already, she was a visiting Tinsley professor here at UT. Since then, she has served as chair and member of many committees for NASA, for the National Science Foundation, for the National Academy of Science, and for Congress. She is the past vice president and century lecturer of the American Astronomical Society. This is the body that is the professional body for all astronomers in the US. In 2012, she received the Cecilia Payne-Gaposchkin Prize from Harvard. And also, interestingly enough, in the same year, she had a comet named after her. And we found out at dinner that this was due to her foundational work as one of the science members of the Big Whole Sky Survey, called the Sloan Digital Sky Survey, that was done in astronomy and really changed our understanding of the field. She's also a long-standing member of the US National Academy of Science and the current chair of the astronomy section of the National Academy. So please join me in congratulating Dr. Bahcall for her achievements, and I will then see the stage for her to give this public lecture on the dark side of the universe.
Thank you very much for this beautiful introduction. It's a pleasure to be here in Austin. Since you mentioned my work at the Hubble Space Telescope, I want to tell you a very short story, and I'm not sure if I told you that the wedding ring, my husband and my wedding ring that I wear here, went up to the Hubble Space Telescope by the astronauts who went there in their last mission, in the SM-4 mission some years ago. And they wanted to honor both John, some of you knew him, and myself for the work that we have done for the Hubble Space Telescope. So on their last mission to the telescope, they took our wedding, they wanted to take something personal. I gave them our wedding rings. John Grunsfeld, the main astronaut who worked on the Hubble, took it there. The rings went 200 times around the Earth, came back to us, and they're right here on my neck. So if you want to see something that went to the Hubble and touched the Hubble, you're welcome to come and take a look at it. So it's a pleasure to be here in Austin again after many years that I've been here before, and it's just wonderful to see the very exciting astronomy program that you have here. I've greatly enjoyed my visit all week this week, from morning to night, talking to the wonderful faculty and postdocs and students in the astronomy department and the research project they work, all the way from the cutting edge discoveries, from looking for new planets around stars to galaxies, to the early galaxies in the early universe, and find out how they formed, to some of the topics we'll talk about today, dark matter and dark energy, to how, what are some of the fascinating fast radio bursts that nobody yet understands what they are. You have some outstanding faculty here, Pawan Kumar, that is working to try and understand what those amazing objects are. So these are all cutting edge research projects in astronomy. So I'm just very impressed with the department and what everybody is doing here in the department. And I'm especially honored to be here today in the capacity of providing the Antoinette de Vaucouleurs memorial lecture. I knew Antoinette and her husband Gerard many years ago. They were pioneers in astronomy. They have achieved remarkable discoveries for astronomy that are still leading us today. So indeed, it's a special honor to give this public lecture today, and the lecture, the astronomy talk yesterday in Antoinette's honor. As already was said, Antoinette was a pioneering astronomer in the early days when women were not really doing much astronomy, very few women. She had a lifelong devotion for astronomy. She devoted her life and attention in detail to research with her longtime partner, Gerard, and they have remarkable achievement. They are really a stellar astronomical couple that are known, well known in the astronomical community. Among their achievement, well, they have traveled the world from Paris to London, Australia, Arizona, Harvard, and settled finally right here in UT Austin and stayed here for the rest of their career. They loved it here. And every time, you know, I think about Austin and coming back to Austin, I do think about the de Vaucouleurs. They were such a power couple here. Some of their discoveries include the local supercluster. They found big structures around our own home galaxy, the Milky Way. They published a big catalog of galaxies, all the nearby galaxies that have been used by astronomers for decades now. And they have measured many other things. They talked about, the first ones to talk about the existence of superclusters, the biggest structures in the universe that we know about are the superclusters, clusters of galaxies. She had a very keen scientific intuition and a very detailed eye to look and discover new things in the astronomical observation. So it is indeed an honor to present a lecture in her honor, and I'm sure she would have been, both she and Gerard would have been delighted to be here today and see what progress has been made in astronomical discoveries by today. So let me now get to the topic. Doesn't want to move. So while the experts are trying to figure out the technical issues here, I'm going to talk about the dark side of the universe. There we go. Excellent. The dark side of the universe. So what is another way to ask the question that we want to talk about is, what is the universe made of? What's out there in space? So we are all familiar with what we call the luminous matter. Stars, and the stars are collected into families of stars, the galaxies like our own Milky Way galaxy. When you go out at night and look at the sky, not like today, it's a little cloudy and rainy today, you will not see very much. But when you look out at the sky, you see the stars in our own galaxy. You look with a telescope, you see other galaxies that are a collection of stars. And the stars all shine, and that's what makes the luminosity that we see with the telescopes. And up to not so long ago, just a few decades ago, we all believed that that's all that exists in the universe. Stars, galaxies made up of stars, and some gas. That's what we see by eye or with telescope, that's all that there is. And we were fine and happy with that. But that is so far from what we understand today. What we understand today, that this luminous matter, the stars and the galaxies that the only thing that we can detect directly with telescopes, with optical telescopes, are a tiniest fraction. They are only a few percent of what exists out in the universe. Maybe only about 5% of what exists in the universe. Think about it, 5%. It's like, 5 people here out of all the people here. Everything else, 95%, is what we call the dark side of the universe. There is dark stuff out there. So what is the dark stuff? And that's what we will talk about today. So the dark stuff has 2 components. And as far as we understand it, they are very different from each other, very separate from each other. One is the dark matter, which everybody, I'm sure, heard of. There is dark matter, something that produces gravity. Matter just produces gravity. But it's dark. It doesn't shine. It's not like the stars and the galaxies that we see. So if it's dark and it doesn't shine, how do we know that it exists? So we will talk about how do we know that there is dark matter in the universe. And in fact, I'll show you that there is much more dark matter than there is luminous matter. Much more gravity in this dark matter than there is in the luminous stars. How much? That's one of the work that as Sharda has said, I've worked on for quite a while, measuring what is the mass density of the universe. How much matter do we have in the universe? How much gravity do we have in the universe per unit volume? So we can measure today quite reliably how much dark matter we have in the universe, how much gravity we have in the universe per unit volume. And I'll show you how we do that. And where is it located? I gave yesterday a whole colloquium about it. I'll tell you very briefly today about it. We can measure now approximately where is the dark matter located and how is it distributed in the universe. So we can answer from direct observation. None of that is speculation. All of that is direct observations about all these questions about dark matter quantitatively. What we cannot answer is what is listed in red. What is the dark matter made of? What is the particle that the dark matter is made of? We know, for various reasons, we'll discuss it briefly, that this dark matter that produces the gravity is not made up of the normal atomic matter that we are familiar with. What we are made of, what the buildings are made of, the chairs are made of, all the baryonic matter, atomic matter, that we are familiar with, we know that most of the dark matter is not that. It has to be some new particle in particle physics that has not yet been discovered. There are many experiments to try and discover it, not yet been detected. And that's one of the biggest open questions still in cosmology. So we'll talk about that. And then the second part of the dark side of the universe is something that, for the lack of a better word, we call it dark energy. That's even a newer discovery, only about 20 years old, and that is a discovery that the expansion of the universe as we observe it, it comes directly from observations. The expansion of the universe, and we know that the universe has been expanding for the last 14 billion years, that expansion is now counterintuitively to what we have all expected, is getting faster and faster. So the universe expansion is accelerating. We expected it to slow down because gravity will pull it back, but we find the opposite. We find that the expansion of the universe, the rate of expansion is accelerating. And gravity cannot do it, just dark matter. Gravity cannot accelerate, it can only slow it down. And there is something else in the universe, in the cosmos as a whole, that makes this acceleration possible. Something that opposes the pull of gravity and makes everything go faster. And we'll talk about that. We call it dark energy. I'll show you how we know that it exists. I'll show you how much we can measure quantitatively how much exists, where it's all over the cosmos, all over space, but what it is, we are not sure. We think it may be the cosmological constant that Einstein has suggested a long time ago, and then was discarded, and it may be raising his head again at a very small value of this cosmological constant. That's one of the possibilities. So we will talk about that. So that's just kind of an introduction of what we are going to cover. And let me also say, if there are any questions as we go along, feel free to ask while we are talking, and just to make sure that it's all clear to everyone. What did you do to make it go?
Some magic, some dark magic.
Dark magic.
I think this is just coming up. I think just use this one. I think it's a pop-up for the internet. So if you just use that. This arrow.
So what do you do? I just
This
push
arrow.
this one?
Yeah, this arrow.
And that will move it?
Mm-hmm. Yeah.
Okay. And if it doesn't, I'll have to call you again. You'll have another job here, huh? Okay, here is luminous matter. Everybody knows this is our nearest neighbor, the Andromeda galaxy. What you see here is a galaxy just like our own Milky Way galaxy, which is a collection of billions and billions of stars. That's all the luminous matter. And the stars produce their energy, the luminosity. How? Why do the stars shine? Who knows? Why do the stars shine? What produces all the luminosity from the star?
Nuclear fusion.
Yes, so it comes, all the stars produce their energy, enormous amount of energy, like our sun, which is a typical star, by nuclear reactions in their core. Hydrogen going to helium and over to the higher elements. So it's nuclear fusion reactions in the cores, in the very hot cores of the stars, in the billions of stars that we see, and that is the light that you see right here. So we have the stars and those galaxies, this one, our galaxy, and all the billions and billions of galaxies that exist in the universe are in equilibrium. Those stars, the billions of stars, they are not flying out of the galaxies, they are not collapsing in, they are in equilibrium. How can they be in equilibrium? You have billions of stars there, they all have gravity, strong gravity. Each one is like the sun approximately, a lot of mass there. So everything is held together, all the stars are held together by the gravitational potential of the galaxies. So why aren't all the stars falling in if you have so much gravity there? Why aren't all the stars falling in, collapsing into a big black hole? Something makes the stars not fall in. What is it? They are moving around all the time. They have a kinetic energy. They have a kinetic energy for the stars that compensate exactly, approximately, the potential energy of the gravity. So you have gravity pulling them all in, but they are resisting falling in, those that survive. Some of them may have fallen into the center and collapsed to the black hole at the center. But most of what you see, the billions of stars, do not fall in because they are moving around the galaxy all the time. So the stars are not static, they are not stable in the galaxies. They are constantly moving around. Our planet Earth, which is, if this was our galaxy, our planet Earth will be someplace here, in inconspicuous place near the side. And right now, we are all moving around on our planet Earth with our sun, moving around the center of our Milky Way galaxy at a very fast speed. How fast are we moving? We are moving at 200 kilometers a second. So every time I say a word, we moved at 200 kilometers. So we are moving very, very fast. And that motion is what compensates the gravitational potential of the galaxies that pulls us in, and that's why we are not falling into the galaxy. This is, for example, the same exact thing as happens in our solar system. We have the sun, we have our planets. Our planet Earth goes around the sun at a specific speed, and it's at the exactly right speed to make us not fall into the sun. If we went just a little bit slower, we will fall in. If we went just a little bit faster, what will happen to us? We will fly out. So you have a compensation. And in astronomy, in many of these objects, it's constantly sort of a tag of war between two forces. You have gravity that pulls you in, and you have some kinetic force, motion, that prevents you from falling in. We say in astronomy, gravity sucks. Why is that? Because gravity just sucks everything in. So gravity always will try to pull you in. That's what gravity does. In order not to be sucked in, you have to move. You have to do something in order not to fall in. So the reason I'm talking about that is because that allows us, luckily for astronomers, it allows us to weigh the galaxies, to measure their mass. Otherwise, we just look at this beautiful galaxy, and if I ask you, well, how much does it weigh? We'll say, we don't know, right? Because you have to have a quantitative way to measure the mass. If you know that the galaxy is in equilibrium, the way I described, so you have the potential energy, which depends on the mass. You have the kinetic motion that equals to it to compensate for it, and you can measure the speeds that the galaxies move. We can measure that very well with a Doppler shift. And then we equate the two, and we know the mass of the galaxy up to some scale. And the reason I'm explaining it, because that going to lead us to the dark matter. Okay, let me try your trick now and see if it works. No.
Try this one. I think we are getting this AT&T thing. We have to
Where do you go?
This one we have to kill each time, and then.
Oh, how do you kill it each time?
When it comes back, I will just come in. It has a red button there. We have to kill it.
Okay.
Okay, let's try it. Can you kill it?
This is weird.
Yes, they've put it on Wi-Fi. I will tell you.
Shall I try another one?
Yes, you can go back and forth now. Yeah.
Okay.
Yeah.
Hopefully that will work. So here is another example of a galaxy. This galaxy is face on, and you can see it's like a rotating. That's called a spiral galaxy. It's like a rotating disk of stars. So you see all the stars and gas and light from the billions of stars. You see the galaxy rotation. They are rotating roughly at the same speed as we are rotating, at about 200 kilometers a second. And again, that's what makes it so that it's in equilibrium, doesn't fall in. So we can weigh the mass of galaxies based on what I just said. Okay, working. So we have several ways of measuring. One is the motion, the simple classical way that I just said. Potential energy equals the kinetic energy approximately, and then it keeps the galaxy in equilibrium. So the motion of the stars and gas, and we can measure the velocity, the speed, the motion with Doppler shift, with measurements, with the spectrograph. And we use the virial theorem or the equilibrium. On the left, Gm, m over r squared. That's the gravitational energy of the mass, of the gravity. Has to be approximately equal to the kinetic energy, the mass times the velocity squared. So we can measure the velocity. We know the radius. We measure up to a given radius. And you see from the top line, the velocity is given by the gravitational constant, the mass within the given radius divided by the radius. So we measure the velocity, we know the radius, so we can weigh the galaxy, the mass within a given radius. That's how we weigh galaxies. That's one classical method, and it's still being used all the time today. Another newer method is gravitational lensing. Gravitational lensing is what Einstein predicted in general relativity. If you have a background source, a galaxy or a quasar in the background, and the light from the galaxy or the quasar on the way to us passes close by to a galaxy or a cluster of galaxies to some strong gravitational potential, the light will be deflected by gravity. So gravity in GR, in general relativity, acts as a lens. It deflects the light, and we'll see distortion of this background galaxy. And I will show you, and we measure it now on galaxies, clusters of galaxies, and I'll show you some of those beautiful images. And that, by general relativity, we can get the mass exactly within the given radius. We don't have to assume equilibrium or anything. It's just gravitational lensing from general relativity. It gives you directly the mass. And what I'm going to show you, the data from both of these methods for measuring velocities of many galaxies, as well as mass from lensing on the larger scales of the luminous galaxies that I showed you, show us that there is large velocities and large mass, large gravity, as you go farther out in the galaxies where you don't see any more stars. So you don't see any more stars where it was dark. We still see velocities, we still see lensing mass. Something is giving gravity there. And that, I should only emphasize, assumes that general relativity is correct, no changes, and that Newtonian dynamics is correct. If you change Newtonian dynamics or GR, all of these arguments will fall apart. So the only assumption is assuming Newtonian dynamics, and if that is correct with Newtonian dynamics, this implies that you have to have a lot of dark matter there because something is giving it gravity, something is giving it velocity. Things cannot move by themselves. Something has to pull them, something has to gravitate them. This one. Here is one of an example done in the 70s. Here is a galaxy, and in the plot below is a measure of what we call rotation curve. How fast is the galaxy rotating as a function of scale? In the center, this is the velocity of the stars, observed velocities. How fast are the stars moving here and here and here and here and here and here and here? No more stars out there by the tails. Beyond that scale, so we see they are moving fast at about 200 kilometers a second, just like our own sun in our galaxy. But when there are no more stars, if there is no more mass there, if there is no more additional gravity, what would we expect for this velocity curve to do? Starts falling down. No more mass, nothing else moving it. We expect it to start falling down in a Keplerian way. That's what our planets do in our solar system. You go farther out, they start moving slow and slow. There's no more extra gravity there. This is not what happens in galaxies. The velocity keeps flat at 200 kilometers a second, not only up to where I show you, but it will go like half the room. It will go flat, up to there. What keeps these velocities high? There are not many stars. Maybe there are some stars there, but not many stars. What is the gravity? There is some gravity that keeps the stars up at this velocity of 200 kilometers a second. And that has to be, if you assume Newtonian gravity, if you don't change Newton's law, and I can tell you that there are a few, maybe a handful of scientists, in case people ask later, there are a handful of scientists that are trying to change Newton's law in order to account for this very strange behavior. Well, we think that both are strange. To have dark matter is strange, but to change Newton's law, it's even stranger. So you have your pick. But we think, most astronomers think that Newton's law is correct, that general relativity is correct, and I will assume that in the rest of the talk. And that means, if it's correct, that means we have to have gravity there. We don't see stars. We don't even see sort of dead stars or things that, may not emit luminosity. So we call it dark matter. It's gravity that keeps this velocity high, but it doesn't shine, so we call it dark. And for some other arguments, and I will not go into detail, other measurements from the cosmic background radiation and from Big Bang nucleosynthesis, we know that the amount of baryons, atomic matter in the universe, has a limit that is much lower than how much gravity we need in order to keep these velocities high. So most of this dark matter has to be not the normal atomic or baryonic matter that we are familiar, not the elements of the that we know of, hydrogen, helium, and all the elements we are familiar. Probably some new particle that we have not yet discovered.
I'm going to reset it so it won't.
Okay. So this is one of the pieces of evidence for the dark matter, are this flat rotation curve that keeps velocities high. There's no other explanation. There are really only two possibilities. Either you change Newton's law, or if you don't change Newton's law, you need dark matter. There's really no in-between ways out of it. So when you look at galaxies like that, let's just put it in perspective, you see this type of galaxy, again, rotating with all the stars. That's a luminous matter. You see, as you go to the side, the stars getting faded away. I mean, there are very, very few stars. And think about this galaxy, or any galaxy that you see now in images or pictures, posters. These are just the centers of very, very, very huge dark matter halos. A lot of dark matter. So this galaxy will be surrounded with, a big part of this room as a dark matter halo. Full of dark matter. So I'm just going to show you a few more galaxies and think about, again, you see the billions of stars, you see some of the rotation of the disk, and think about all around it is surrounded. And it's not just all around it, it's also inside the galaxy. So I don't want you to think about the dark matter as being like a donut, around there. Dark matter is everywhere, including in the center of the galaxy. We measure the density of the dark matter from gravitational lensing and other methods to just drop from the center far away, but it extends all the way, as we said, to these very, very dark, large dark matter halos that can extend to 100,000 of light years from the center of the galaxy. Hundreds of thousands of light years. If you turn a light on in one side of the galaxy, take hundreds of thousands of years to reach to the center. That's what light years mean, right? So this is where the dark matter is. Yes?
Can you tell if the distribution of dark matter in those situations is symmetric? Is it stochastic?
That's an excellent question, and people have been, it's not easy to tell, but so far from what we see from, mostly from gravitational lensing observation, is that the distribution of the dark matter is it's not fully spherical, but it's more kind of elongated in the line of the elongation of the galaxy, but not as elongated. So this one will not be as elongated, but it will be kind of like a big fat football. Very big, huge. It's hard to measure because only with gravitational lensing you can do such measurements to try and trace the dark matter. Here you see two galaxies that interact. Galaxies, sometimes if they are close together, their gravitational pull will pull them together, they'll interact, they will gravitationally harass each other, and stars will be flowing out of it, and you see a stream of stars flowing out of it. And the dark matter halos also come together and interact. Eventually they'll become one big galaxy with a bigger dark matter halo. By the way, our galaxy, the Milky Way galaxy, us, our home, and our neighboring galaxy, Andromeda galaxy that we just saw before, are headed for that. Measurements show that we are moving towards each other, and our dark matter halos may already be touching each other, and so don't worry, it's not so soon, but in about 4 or 5 billion years from now, we will merge together with our neighboring Andromeda galaxy and eventually become one big galaxy. But we have some billions of years to wait for that, before that happens. So the picture that I want you to think about galaxies, again with the assumption of Newton's law being exact, is that we have a seed, a central core, that is the luminous galaxies that you see, and they are very big, but they are just the core of a much, much bigger dark matter halo. So one thing I can just briefly say, because you may wonder, well, how come all the stars are at the center and the dark matter, even we have some dark matter in the center, dark matter goes much farther out. How come? What separates them? So let me just give a very brief explanation to that so you won't be puzzled by that. Is what we think originally is we had these dark matter halos in the very early universe. The gas, which was existed in the universe, the atomic matter, which we can measure how much existed, it's about 16% of the total mass, fell into these dark matter halos by gravity. Some of it cooled down, so the gas, the baryons, as you know, gas can dissipate, interact with each other, lose energy, and then fall more to the center. There it cools by various mechanisms and forms some stars. So the reason that most of the stars are in the center is because the gas has this property of dissipation, and it can lose energy and dissipate. The dark matter does not. We don't know where the dark matter is, but from this observation, we believe the dark matter does not dissipate. Otherwise, it will be also at the center. And that's why the stars are mostly at the center and the dark matter is farther out. But this is a picture of dark matter. So when we see these amazing, beautiful galaxies, think about them as just the cores of this much bigger system. Here is a cluster of galaxies. So almost each yellow image here is a whole galaxy. And this is a family of galaxies. They are called clusters of galaxies. They are the biggest system in equilibrium in the universe. They are the most massive system in equilibrium in the universe. And you see this blue kind of almost partial circle going around. Who knows what it is? What is this blue thing that goes around? Anybody knows what this blue is? Beautiful blue image. This is a gravitational lensing effect. That's Einstein GR in action. So this blue galaxy, this blue image that you see, is a background galaxy, a very young galaxy in the early universe. In the early universe, the galaxies were bluer because they had younger stars. Blue galaxy. The light, it's one galaxy. It's not many, many, many that you see. It's one galaxy that is right behind the cluster, way in the background, and the light from that blue galaxy on the way to us passes this cluster of galaxies. And the light, when it goes by the side of the cluster of galaxies, get bent by Einstein's general relativity, by gravitational lensing. And when it comes to us, it looks distorted. The galaxy looks distorted, and that looks like what we call in general relativity the Einstein ring. It breaks the same galaxy. You see it in several images all around the cluster. That's general relativity in action. You see the light being lensed by the cluster of galaxies. And based on GR, the amount of distortion and the radius tells us exactly what is the mass in the cluster within this radius. And the mass in that cluster is fully consistent with the mass that we'll get from the velocities that I mentioned before. and it shows that we have a lot of dark matter, as much dark matter as we said before exists in the galaxies per unit galaxy. So you are surrounded with a huge amount of dark matter. You see it from velocities, and you see it from gravitational lensing. So using gravitational lensing now on many clusters and groups and galaxies, we can measure the mass. Let me show you some of those images because they are just stunning. I think they are just so beautiful. This is another, some of them are from the Hubble Space Telescope. I'm not sure if this one is. Yeah, this is from Hubble. You see again a cluster of galaxies. Look at that beautiful gravitational lensing. And it will always look a little blue because it's always a background galaxy. And measuring the distortion and the circle or partial circle, you can get the mass there, and you see how much dark matter or total matter exists, and it is much, much more than the mass that exists in the galaxies. Look at that. That's called a smiling cluster. I think that's a very cute name for that cluster. That is again from the Hubble Space Telescope, and you see this is not a very rich cluster, just a few galaxies, but look at that beautiful gravitational lensing, and it tells you exactly how much mass exists. So from these measurements of gravitational lensing, well, here is another more recent one from the Hubble Space Telescope. The image, you see the galaxies, and the contours are the gravitational lensing measurement that are measured from the Hubble telescope. It just represents all the elongation and the partial arcs, and you can see how much dark matter exists there. You can measure the amount of dark matter. So let me skip that. So let me go to, just to summarize the part on dark matter. So we talked about dark matter. How do we know that there is dark matter? We said it's dark, we cannot see it, but we see its gravitational effect on other systems, on other stars, on the motions of galaxies, or gravitational lensing. So we know it by gravity, by motion, or by lensing. It's very clear it exists. Where is it located? We find it mostly in big halos around galaxies and in clusters of galaxies. So it's distributed on the large scale following the galaxies and clusters of galaxies and superclusters and so on. Those objects, those systems that the Vaucouleurs worked on for most of their lives. So they are full of dark matter. How much? When we do detailed measurements, and I'm not going to go to the details of it, but that's a type of work that I've been doing for a while, we can measure from different methods that I showed you, following the dark matter with lensing and other methods around galaxies and clusters and going to larger and larger scale. We can measure that about 25% of the critical density of the universe is in dark matter. So what, and I talked yesterday at the department on that. I will not go to the detail of how we measure it, but it's based on all the measurements that I described now. Now, what is the critical density? Because if I give you the mass density per unit volume in some grams per centimeter cube, it will not mean very much. So we usually measure it in units of the critical density of the universe. That comes from Einstein's equations for the universe. The critical density of the universe is the following. We know that the universe is expanding. Hubble found it many years ago. The universe, all the galaxies are receding away from each other, shows that the whole space and time is being stretched out. It's expanding at rate that is now measured quite accurately. So the question becomes is, the universe started expanding 14 billion years ago from something we called a Big Bang. Something happened 14 billion years ago. We don't know exactly what, but something happened that started creating all the matter in the universe and spreading everything out. And the universe has been expanding since then. And the question is, what will happen to that expansion? What dominates this expansion? So on one thing, you have some force that gave the expansion its push, its velocity of the expanding universe. And think about the gravity inside the universe. And think about, we said in astronomy, we frequently have this tug of war between two forces. Gravity sucks you in, and you have some motion that goes against it. Here we have the motion of the Big Bang is pushing everything out. We have the gravity in the universe, all the galaxies, and the stars, and we, people. I mean, everything is gravity. What do you expect will happen in the future of the universe to this expansion, with this tug of war? What will happen? What would gravity do? Exactly. So gravity, the only thing it could do is slow the expansion down. So gravity can slow the expansion down. If the gravity is low, it will not. So if the gravity is, so the critical density of the universe, I forgot my train of thought. I was talking about critical density. So if the universe has the critical mass density, by Einstein's equation, it's a fixed number, that means the universe will neither recollapse nor expand. It will expand up to some scale and just at infinity will saturate. If the gravity in the universe is above the critical density, means gravity will win and the universe will recollapse because we are giving some Big Bang velocity. If the mass density of the universe or the gravity in the universe is less than the critical density, then the universe will expand forever because you don't have enough gravity to slow it down. So what we found and others, that the total mass gravity in the universe is only 25% of the critical density. And that already tells you that the universe will expand forever. Not enough gravity, it's well below the critical density, and therefore we don't have enough gravity to stop the expansion, so the universe will expand forever. So that's how much mass we have total, 25% of critical, but we have a limit from other observation that the atoms, the luminous material, like baryonic material, is only 5% of critical. So we know that most of the dark matter has to be non-baryonic, non-atomic, has to be some new particle in particle physics. And there are many experiments currently being done both underground to detect these dark matter particles locally, because we have dark matter here. Presumably we have some dark matter here in the room, but we don't find it, don't see it. Just to show you that maybe it's not so surprising not to feel the dark matter. We think, how can you be dark matter? If you had bricks here, we will see them. We are all familiar with neutrinos, you know, the little tiny particle that is almost massless, not quite massless. It does have a little mass. Right now, we are bombarded with billions of neutrinos every second, all the times. And do you feel it? No. And the dark matter particle may be something like that. It will not be neutrinos, they are excluded for other reasons. But the dark matter particle may not be something that we will see or feel. It can go through us all the time, some weird new dark matter particles that has not yet been detected. And there are many experiments to try and detect it. Unfortunately, and it is a little frustrating, nothing has been detected yet. So I cannot share with you the good news of detection of the particle. So we don't really know what the particle is, but it is one of the most fundamental questions, not only for astronomy and cosmology, but for physics. What are the particles that we are missing in physics? So it's a very important, open question, and hopefully, we will find it from one of the big experiments currently being carried out. So here we answered all the questions except for the last one. So we have progress and we still have some ways to go. Let me move on quickly just to the dark energy side. So what is the universe doing? We talked about the universe expansion. If we plot the size of the universe, and we can measure the distances to galaxies, distances to objects, as a function of time. Right? So the universe, we measure it to be expanding. The distances to galaxies grow, that's Hubble's law. Distances to galaxies grow with their redshift or with their time away from the Big Bang. So the Big Bang happened someplace here. We are now someplace here. And depending on, as we said, what is the gravity, the mass density of the universe, the gravitational potential in the universe per unit volume, it will tell us into the future if we have what we call a closed universe, if the density, gravitational density is bigger than the critical density, the universe eventually will recollapse. If we have the critical density, it will just go to infinity and just stay there. And if we have an open universe less than the critical density, which is what we measure only 25% of the critical density, we call it open universe, and it will expand forever. But as you said, if we just have this gravity, even if we have only 25% of the critical density, and the universe will not recollapse, it will slow down. The expansion will slow down, because that's the only thing gravity can do, right? Gravity will suck it in. So even 25% or 30% will slow the expansion down. And here is a beautiful thing. About 20 years ago, two big teams of astronomers, people have tried it for many, many decades, but two teams succeeded in measuring what we call the slowing down of the expansion rate of the universe. It even has a name. It's the deceleration parameter. How fast the universe is slowing down, because that's what we expected. That the expansion rate, it's expanding, but the rate of expansion we expected to slow down because of the gravity. And if you had the mass density, the critical density, it will slow down a lot. If you have it only at 25%, it will slow it down less, but nevertheless, it will slow it down. And the amazing surprise that both of these teams found independently, not talking to each other, I mean, they were competing, so they kept it very close to the vest, but they found the same result. They found very surprising result, that the expansion rate not only does not decelerate at the rate we expected, but that it accelerates. It goes faster and faster. So if you plot it here, it will be the red line, but going faster and faster. So it's just accelerating. Now gravity cannot do that. Gravity cannot. It's like if I take a ball now in my hand and throw it up in the air, well, we all know what will happen. It will go up, 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 depends how fast I throw it. It will stop at some point, right? It will slow down. Why? Because gravity. It will slow down, stop, and then what? And then will fall. But it will slow down when I throw it up. If I throw the ball now, and what you will see is that the ball all of a sudden starts going faster and faster through the roof and into the space and into the sky, faster, faster, you'll understand that gravity cannot do that. That you need some other force to make it go faster. And that is the dark energy. That's what they found. So they discovered it in 1999, so that's about 20 years ago, and the discovery is so fundamental, so mind-boggling, that they have already received the Nobel Prize for that a few years ago, for discovering of the acceleration of the expansion rate of the universe. And I want to show you some of their results. It doesn't look very impressive. They're scattered there. It doesn't look very impressive, but it is significant and very important. So what you can see here is the distance to the object, that's a Hubble law, the expansion rate of the universe. The distance to this different object, they use supernova as what we call distance indicators. I will not go into the details. If you have questions, I'll be glad to answer it. But they measure accurately the distance to various objects as a function of their time, looking at higher and higher redshift mean to earlier and earlier time in the universe. And you see the expansion, the Hubble law. And back at the very earliest time, there are different curves. And those depend on how much the mass density of the universe. And if you have a lot of mass density, the universe will slow down, and the dots will have to be on the lower curves. The dots are their measurements, will have to be on the lower curve. If you have less, if you have only 30% of mass density, it will be a little higher. But what they find is that the distances are larger at the higher end, which require you to have something that overshoots the gravitational pull. We still have the gravitational pull of the 25%. That doesn't go away. But you need something that is more than the 25% opposing the gravity in order to make it accelerate. And that's what they found. That was a discovery of acceleration of the universe and the introduction of dark energy. Here is a more recent feat of hundreds of recent measurements, and the underlying line, you see it's curving up. The underlying line is that model with the dark energy that contains about 70% of all the stuff in the universe, all the energy density of the universe. So we measure that there is dark energy, something that accelerates the expansion rate of the universe. We can measure how much it is from these measurements. So we have dark matter that is about 25%. We have dark energy that is about 70% of all the energy density in the universe. And the little baryons that we are familiar with, what we are made of, is only 5%. So 95% what's out there is dark. Most of it is this mysterious dark energy. And the line, the black line that goes to the point that curves up to larger distances, is that model with a 70 or so % dark energy, 25 dark matter. So you see the data is remarkably good and fits it remarkably well. So dark energy, the measurements show that the universe is accelerating. Dark energy is stretching out. It's opposing the pull of gravity. It has to oppose the pull of gravity. It's stretching everything out, whereas the mass density pulls you in. Here are some of the measurements that they measure, and the total amount in the dark energy is 70% of the critical density. And what is it? Well, we don't know. Just like with dark matter, we don't know. We think one of the possibilities, sort of supported so far by observations, that it may be the cosmological constant that Einstein suggested many decades ago, which is that it's a property of space itself. It's a general relativistic effect that every piece of volume of space, any place, has some energy that opposes the pull of gravity. It's a quantum fluctuation effect. It's like quantum pairs of particles continuously created and annihilated in vacuum itself. So vacuum is not fully vacuum. So vacuum is not nothing. There is some energy there, and it's energy with a negative sign, so it pushes everything out. And all of space would have it. And it's noticeable, mostly, it will have it here too, but it will not be noticeable. But it will be noticeable only on the very large cosmological case. So it is a complicated quantum fluctuation, general relativistic effect, but it's a puzzle, not only to cosmologists, but to physicists. Why do we have it, and why is that value that nobody has expected? If originally people thought there may be a cosmological constant, but then it will be very, very large based on just fundamental principles, but because we didn't see it, because if it was so large, we wouldn't have a universe. The whole universe would have expanded very quickly. Then we thought, the physicists thought, okay, it cancels to zero. Now we find, well, maybe it's not canceled to zero, but it cancels mostly, but left a little bit to cause this acceleration of the universe. So this is the second most fundamental open question in astrophysics and cosmology and physics, is what is this dark energy? Is it the cosmological constant or not? Or do you need to change general relativity by a little bit to account for that? Most people don't think you change general relativity, but that is still something to consider. I just want to finish up. So the content of the universe is this pie diagram. The baryons, what we are made of, is the tiniest part of it. 25 or 20% is this exotic dark matter, new particles. Most of it, 70 or 75%, is this mysterious dark energy that may be the cosmological constant. So 95% is dark. Well, the cosmic background radiation, I'm going to skip it because I think we're running late, supports it extremely well. These are beautiful early remnants of the Big Bang that, if you look, I will not talk about it, this is data from the microwave background radiation. Look how beautifully it supports the red line, which is that model of dark energy and dark matter that we talked about. So let me summarize. What is the content of the universe? Only 5% is the baryonic matter, stars and gas. Dark matter, 25%, probably new particles, and we better find it sometime soon. Dark energy is 70%, maybe a cosmological constant. We are not sure yet. Really an open and exciting question. Or keep in the back of your mind, maybe has to change GR. Less likely, but we have to keep an open mind. So what does the universe look like? It looks like that. It looks mostly dark, and about 5% is the light, or the baryons. Or if you want something a little more appetizing, dark matter is the base. It's most of it. The base of that cupcake, chocolate cupcake. You have dark matter, which is a lot of it, the frosting, but much less than the dark energy. And the little baryons are the little berry on the top of it. So the baryons are just a tiny little part of everything. So what is the fate of the universe? The universe will expand forever. First of all, we don't have enough dark matter. That already tells you we'll expand forever. If we have an acceleration, cosmological constant, it will make sure it will expand even faster and then finally rip apart. It will get larger and larger. It will get sparser and sparser. The distance between all the galaxies will get larger and larger, so everything will get very sparse. It will get very dark because galaxies will be farther away. Stars will die off their life cycle, and it will get colder and colder. So it's not a very happy ending, but again, not to worry. It's going to take many, many, many billions of years to reach that. Thank you very much.
Okay, so questions for Dr. Bahcall.
This is a question about throwing the ball up in the air and it, for some reason, accelerates instead
Yes.
of falling down. And that because of repulsive force pushing it out,
Yes.
or because of an attractive force.
That's correct.
We can see. So
Correct.
have we ruled out that there's a dark matter halo around the universe that is making it?
That's a very good question. I get that question frequently, and it's correct. My analogy sort of says, oh, maybe somebody is pulling it from out. The answer to that is no, we don't see anything pulling it up, and I'll give you some reasons for that. First of all, when we measure the acceleration from everywhere, we measure the same amount of acceleration in any direction. So you don't have something pulling you in that direction. So that's already rules it out. Now, could it be something pulling you out from big dark matter halo all around us? I didn't think about something that is from all around you, but then you will see some other effects on gravitational pull when you look at some of the early galaxies in the universe that are farther away, and we don't see it. And what we do see with this dark energy, we see that it's most effective in recent time. It only in the last maybe a billion years, maybe less, and it was not very effective early on. It changes with time as expected if it's a cosmological constant. And we actually, when we go back at very earlier time, we see the universe start decelerating as we would expect as we go to early time, because at earlier time, the universe was smaller, the dark matter, the matter density was tighter, it became more dominant than a cosmological constant that doesn't change with time. So as space was smaller, you had less of a cosmological constant energy, but more of a mass density, right? So as the universe was smaller in early times, the gravity was stronger because everything was condensed. We are not creating new matter. The mass density was smaller, the mass density was higher, but the cosmological constant is just a property of space. It's being created by itself. As space increases, you have more and more and more. So when the universe was smaller, you had much less dark energy, much more dark matter. So we actually see the deceleration. If we have as much dark energy then as we have today, the universe would never exist because it would have ripped apart. Galaxies would never form.
Yeah, if you took the distribution of dark matter that's been observed in some other galaxies and assumed that the Milky Way has the same distribution of dark matter, then how much dark matter would there be in our solar system?
Oh, that's a very good question. In our solar system, we don't see very much, and maybe a very minute thing that will not affect. We can even measure it from detailed dynamical motions of the planetary systems in our solar
system. To the mass of the Earth, or more or less?
So, say it again?
I'm asking, would the amount be equal to the mass of the Earth?
It will be less. It will be less in the solar system. And people are debating how much dark matter, not the baryonic matter, exists locally, not in the solar system, but close enough to us, because the experiment that we try to measure has to detect dark matter, well, actually here on Earth, underground. So it's very hard to get it directly. If we get the dark matter, we look at other galaxies exactly as you say. We measure from lensing and the other measurement the distribution of dark matter all the way from the center to the outskirts. The problem at the center is the following. There is dark matter in the center, but the problem is that at the center we are so dominated by stars and baryonic matter that it is a little bit difficult. It's uncertain to separate the dark. We measure gravity, the total. Then we have to separate all the baryonic matter, all the stars and so on, and that's where the density is high, either at the center or even near us. The density is high and try to separate. But astronomers do as good a measurement as they can in the local vicinity of our Earth in order to detect the dark matter particles. And maybe the reason we have not yet detected it is maybe the density is lower than we expect.
So a given area would have different percentages of dark matter, dark energy, and atoms?
So the dark energy, let me start with the dark energy. If it's a cosmological constant, the constant means it's constant per unit volume. So any unit volume will have, in the space itself, will have the same amount of dark energy. So as you go to bigger and bigger volume, you'll have more and more dark energy. As the universe expands into the future, it will be bigger, it will be more dominated by dark energy than it is today. The dark matter density will go down, the dark energy density will go up as the space increases. It's just per unit volume, you have the same amount of dark energy. if it's a cosmological constant. The amount of baryons and dark matter changes from place to place locally within a galaxy. So in the center of a galaxy, we have some dark matter and a lot of baryonic matter. That's where you see all the stars. As you go farther to the outside, you have much less stars, much less baryonic matter. You have a lot of more dark matter. But the density of both decreases from the center going farther out. The density always decreasing from the center of the gravitational potential well, decreasing out both for dark matter and for baryonic matter.
If the expanding universe and therefore more and more space means more and more dark energy, doesn't it violate the law of the conservation of energy?
No, because that's a good question. No, that's because in GR, with this dark energy, you are creating space itself. And as you are creating space itself, it is proper with general relativity that the dark energy will be increasing.
Since Einstein assumed that you had a static universe, what are the implications?
Say it again?
Since Einstein assumed that there's a static universe, what are the implications for GR if you have an expanding universe?
Well, and that's exactly what happened when Einstein, which is really quite an interesting story by itself, when Einstein developed his equations for the universe, he believed wrongly at that time, it was before Hubble discovered, just a few years before Hubble discovered the expansion. Einstein and everybody else at that time believed that the universe was static. So when he developed his equations, he saw that the universe didn't seem to be static from his equation. And that's when he introduced the cosmological constant to compensate for the expansion or deceleration of the universe to keep it constant. And after the Hubble discovery was that the universe is expanding, the rumor at least said that Einstein said that was the biggest blunder of his life to put in the cosmological constant there, because he could see from his equation that the universe was not static, but everybody assumed that it was static. It's a good lesson in history. Whatever we assume today about what we think we know, including everything I told you about dark matter, dark energy, may change in 50 years or 30 years or 20 years, We have to always keep an open mind and see what the data is telling us and try to fit again the theory and explain what the data is telling us. Yes?
What are the tools that we'll see in the near future that will give you more data about dark matter and dark energy? The GMT, is that something that...
Yes, so they are really fortunate for astronomy. They are really important new observations, observatories and tools in many different ways. The GMT and the large telescopes are obviously critical for finding, the smallest galaxy, trying to understand better dark matter, trying to understand the evolution of galaxies, which also indirectly tell you about the dark matter and its properties and so on. So going to the large telescope is a very critical importance. As you know, the Europeans are doing it already. United States is starting to lag behind. So it's really important for us to move on with those big telescopes. There are other observations that are very critical to determine dark energy, because it's a fundamental question. And for that, again, Europeans have some space missions. I know here in Austin you have the new project, the HADEX, to measure properties of dark energy. That will be critically important to measure, because you can then measure the detailed property, how much the dark energy is changing with time. And you find that it's constant with time, or what we call the equation of states of dark energy. If it's constant with time, with equation of state of -1, that is a property of a cosmological constant. And that's what we try to measure in astronomy. Because to understand the dark energy from physics background is very difficult. It's very hard to know for physicists where to go. So we try from astronomy to help with what we can to measure everything possible to help understand what it is. So, for example, the HADEX project will measure the dark energy properties as you go to the higher redshift, and therefore how much it's changing with time. So those are very important. And then we have all the very important direct measurements to detect directly detect dark matter particles, heating detectors underground, some of it being done in the United States, a lot of it is being done in Europe. Those are continuing and are critically important to understand that. Until we detect something, both in dark energy and in dark matter, it's going to be hard to finish the story. So I'll be glad to come back once we find it and tell you the end of the story.
So I should mention something. We are happy to stay as long as you have questions, but I know some of you have to go because of the time. So if you have to go, feel free to go, but others feel free to stay as long. Neta has said she will answer questions as long as they come.
Yeah. As I understand the graph you showed us, it's the observational evidence for dark energy. You're comparing distances with redshift to what, type 1a distance measure?
Correct. It's distances obtained from the supernova type 1a.
Type 1a.
So they are used as what we call standard candle,
right,
that you know what their intrinsic luminosity is. And if you know the intrinsic luminosity, you measure the apparent, what we measure here on there, that tells you the distance. Like if you know you have a 100-watt bulb, by measuring how faint it looks, the flux, you know the distance. So we use them
But
as...
It's the divergence between a redshift measurement and the type 1a measurement that is the evidence for dark energy?
No, the evidence for dark energy is, we
is
know
the
from
point.
Einstein's equation what the relation should be between the distance to an object and the redshift. That's Einstein's...
Always constant.
And in those Einstein's equations, the cosmology comes in. How much dark matter, how much gravity, how much is the mass density, how much is a cosmological constant or some other dark energy, and so on. So those are the lines that are plotted for different lines. What is the expectation for the expansion? Using Einstein's detailed relations for given mass density and dark energy density and so on. And what they measure, the distance, are the points that were plotted on the plot. And they show that the distances fit the distances that would require dark energy. In fact, require more dark energy than mass density in order to overcome the pull. The pull always exists. And they have to require dark energy that is more than the dark matter in order to create these higher distances. And the higher distances are given by Einstein's equation based on the connection to the cosmology. I don't know if I explained it well enough, but I'm happy to discuss it more after the talk. Yes. Oops.
I just read yesterday that the two events that I know you're familiar with, and there were two occasions where neutron stars collided, and we were able to measure the gravitational waves that
Yes.
resulted. And I read that the results from those two collisions backed up what you're saying about Einstein's prediction, that it seems to back it up and give an even more accurate measurement. Is
Yes,
that true?
yes. Clearly, one of the really spectacular discoveries in the recent century is the detection of gravitational waves with LIGO. And they have discovered, in 2015, they discovered first time ever Einstein's prediction of gravitational waves. Has never been detected before. It's an amazing experiment. They have already won the Nobel Prize, by the way.
I read that.
And now they detected first black holes colliding and merging, and now they detected for the first time two neutron stars colliding and merging.
My question was, I just read yesterday, I guess, that they think they can use those measurements
Correct.
to more accurately measure the Hubble expansion.
Correct, very, very correct. That's a very new and interesting and original technique. They can measure it as a standard candle. So if they can detect it, another one like that, they already did it with this one. It has a gravitational wave standard candle. They call it standard siren because it's gravity waves. It's a standard siren based on Einstein GR, so they know based on the mass of the object what should be the strength of the siren. And by measuring it, they would know the actual distance.
And how fast it's going.
And how fast, yes. And then you measure, you have to find the galaxy in which it happened and measure its redshift. That's how fast. For how fast it goes, that you have to get a galaxy and measure the redshift, so you know how fast away it's going. But then if you have the redshift and you have the distance, you put it on that plot. So it's the same as supernova. And they find consistent result. That is a beautiful, beautiful result.
Can you explain why you said with such conviction that neutrinos have been ruled out for the particle that is dark matter? I've heard other lecturers suggest that that's one possibility.
That's a very good question. So let me say, when I say it's ruled out as being the major part of the dark matter that we are missing. Clearly, neutrinos have a small amount of mass, and pioneers work on it. John, my husband, has been one of the founders of working on solar neutrinos. So we know that neutrinos have a little bit of mass. So we know that neutrinos are actually a little bit part of the dark matter. So when I say neutrinos have been ruled out, I didn't mean that they don't contribute anything. They do contribute some. But they've been ruled out as contributing the full 25% of the dark matter. Because if it was neutrino, and originally, 10, 20 years ago, we thought neutrino would be a possibility because neutrino, at least it's a particle we know exists. The other ones, we don't even know anything that what they exist. So we were really hoping neutrinos could do it. But neutrinos is what we call hot dark matter because they are relativistic. They move very fast. And the astronomical observation that I just showed you, that the dark matter follows, condensed in galaxies and in clusters of galaxies, will not fit with neutrinos, which is hot dark matter, because what will happen, they move so fast, they are relativistic. If it's the full dark matter, or most of the dark matter, they will stream out. So they will not condense around the galaxies, they will be even farther out into the intergalactic space.
And is the reason why it couldn't be a slower moving neutrino because the neutrino would decay?
Because neutrinos are fast moving particles, they are hot particles. So that's why the current model talks about mostly cold dark matter, which means it doesn't move it's not relativistic, it's sub-relativistic. Because otherwise we will not have the clumping of the dark matter that we see. The hot ones will just stream out. But we originally thought and wanted neutrinos to be dark matter because at least we knew the particle existed.
Any more questions for Dr. Bahcall? You have one more? Okay.
So, sort of following on his question, you said that dark matter didn't cool and condense into forming structures like in a galaxy, like the ordinary matter does. That the halo is much bigger. So.
It does form like the others, but there is some difference. So you have the dark matter. We think it doesn't dissipate. Again, we don't know for sure the particle is, but based on the astronomical observation, we think it does not dissipate. Therefore, it stays the dark matter on those halo. And the gas particles that fall onto it, the baryonic matter, because of dissipation and losing energy, falls more to the center.
So does dark matter will it interact with matter like stars to become part of stars? If dark matter fell into a star, would it add to the mass of a star? And I guess I assume if a dark matter particle hits the event horizon of a black hole, would it stay in the black hole, or is it?
Well, if the dark matter particles hit the black hole, it will get into the black hole. I mean, the black hole, you cannot resist. You get in close, you fall in, and you're done. So you stay there. We believe, again, we don't know the answer, but we believe that dark matter particles only interact gravitationally with other systems. People are trying to modify it now, mostly because we've not yet detected the particle, so we don't know exactly what it is. But the principal idea, we think it only interacts gravitationally, not in any other way. So anything that does gravitational pull, that will affect the dark matter. We don't see any significant amount of dark matter in the star, in our sun. I mean, I don't know what measurements there are. I mean, Pawan would know more, but we don't see any amount of dark matter in the sun. I don't know if it's zero or what the limits are.
Very small and very interesting work done by John and David Spalker have put very nice limits on the total amount of dark matter in the sun. There was a proposal, it's a little technical. There was a proposal that could it be that one of the solutions is something called solar neutrino problem.
Yeah.
Huge big problem that, in fact, John Bahcall pioneered, meaning he discovered the problem, and then one of the solutions that was proposed is that you can somehow cool down the central region of the sun, lower the temperature, produce fewer neutrinos. And that suggestion was that maybe it's these dark matter particles. That's ruled out.
So it's a good question. Why aren't there, more dark matter that we can think of in the sun? Or maybe we don't fully understand the dark matter properties on those small scales. It also a little bothersome that we have not detected it here on Earth in the underground experiment, that you ask about. We would have expected, if we think what the original thinking that it was this kind of heavy dark matter particle, a few hundred GeV, we are at the threshold where we would have expected to detect it, and so far no detection, and it's not exactly clear why. It could be that the dark matter is something different, very light particles, not heavy, not neutrinos, but not heavy particles. Some people are talking about very, very light possibilities. So it is a huge open question, which unfortunately we don't have the answers to that, but those are all puzzles connected into the question of what is really that particle. And I should also say, as I'm sure you know, that the Large Hadron Collider in CERN in Switzerland, other than the Higgs particle, has not yet discovered other tails or other particles they expected to discover. And they don't even see a tail of some of these heavy particles. So that also fits within, well, where is, what is the dark matter? So hopefully with the LHC, they are now going up in luminosity, and they will restart again. Hopefully they will detect something. We really hope that, at some point, a detection will be made either with the Large Hadron Collider or with the direct detection experiments, because otherwise we are left in a big puzzle. Some all my colleagues says, well, it will be more interesting if they don't find something, because that means it's something new. And I really reject that, I think at some point we need to, it's been decades now since we've been looking for dark matter. I think we need to find the particle, solve this question, solve that problem, and move on and try to solve dark energy and solve something else. We can't stay with the same problem forever. We need to, it's such a fundamental problem. If you think about it, we are surrounded, most of the mass in the universe is this dark matter, and we cannot find it. And that's a little mind-boggling. And that some people, out of desperation, try to change Newton's law. It's out of desperation.
Okay, so we have to take Neta to another event. So let's give her a round of applause again.